going to do some physics. I'm going to do some AP physics. And why is this AP physics? Because I said so. This is the book we use for that class. I'm going to do 1 through 17. It's in Chapter 2. So what are we talking about here? Before I even look at the problems, we're talking about constant velocity stuff here. So what I'm looking at here is a couple different ideas. The constant velocity of something is equal to displacement over time. Because it's constant, I can just actually find the slope there. I don't need to worry about calculus. And I also have this model where if you want to know the position of something, oops, that's a plus. Then this is like the equation for the straight line that describes its position versus time graph. Right? It starts out at some initial position, and it moves along with a slope of rise over run, x over t, that's its velocity. And that's going to be straight because it has a constant velocity. So it's like a super fast summary of the notes there. Okay, so let's get into it, see what happens. During a hard sneeze, your eyes might shut for half a second. If you're driving a car at 90 kilometers per hour, during such a sneeze, how far does the car move during that time? Okay, let's see. I think I could do that. I think I need units. Another way of writing this, of course, delta x is equal to vx times t. So I think I have these things here, but I can't just multiply them together because I don't have the right units. So I either need to go to seconds or I need to go to hours. I think it probably makes more sense to do seconds here. So let's see. This is equal to 90 kilometers. Maybe I'll do meters per second. How about if I do that? Little dimensional analysis. 1 hour is 3,600 seconds, and 1 kilometer, I'm putting that on the bottom so it cancels with that, is 1,000 meters. All right, and where'd my trusty calculator go? There it is. So I got 90 divided by 3,600 times 1,000. It's 25 meters per second. And then, according to this, my delta x is equal to Vx times delta t. I'm going to write that out because I haven't used that many times, so just getting used to it. 25 meters per second times half a second. That's 12.5 meters. Right? If you look in the back of our book, I think it says 13 meters there. So why did they do that? Well, these numbers were given with 2 significant digits, so they stuck with that. Although you could argue that the 90 only had 1, so whatever. I'm not going to fuss at you about that. But please include somewhere between 2 and 4 significant digits, not more than 4. That's where it gets offensive. Number 3, an automobile travels on a straight road for 40 kilometers. At 30 kilometers per hour. It then continues in the same direction for another 40 kilometers at 60 kilometers per hour. What's the average velocity of the car during the full 80 kilometer trip? What's the average speed? And then graph x versus t, indicating how the average velocity is found in the graph. All right. So first, what do we got here? I'm going 40 kilometers at 30 kilometers per hour. And then I'm going another 40 kilometers at 60 kilometers per hour. If you think you're all clever and you're like, oh, 45 kilometers per hour, that's the average, you are wrong. Because, well, you'll see why in a second. So if you're going 40 kilometers, 30 kilometers per hour, let's take a look at this. So that's my distance. So I've got 40 kilometers equals 30 kilometers per hour times time. So the time here is, if I divide that over to the other side, that's going to take like 1.33 hours. And then here, 40 kilometers at, if I do the same thing, 40 kilometers is equal to 60 kilometers per hour. So if I divide that over, that's going to take 2/3 of an hour. Right? Okay, so how do we find in part A what's the average velocity? So velocity average is just your delta x over your delta t, but it's for the whole trip. So what's the delta x of the whole trip? I went 40 and then I went 40. So that's 80. Notice that it says it went in the same direction. It's not turning around. If it went 40 and then turned around and went 40, then my delta x would be 0, that displacement. But it says same direction. And then the total time, that's 2 hours. So the average is actually 40 kilometers per hour. Why is not 45 if you're going 30 and then 60 for the same distance? Because you did this for more of the time, so it gets dragged down by this. If that seems super counterintuitive to you, then you could take that to the extreme. If you went to Charlottesville at 1 mile an hour, and then let's say you drove another 60 miles up Route 29 or something at 60 miles an hour. Well, you'd spend 60 hours. If you're doing 1 mile an hour, it would take you 60 hours to get to Charlottesville and only 1 hour to do the rest of the trip. So what's your average speed? It's not halfway in between 1 and 60. The 1 mile an hour dragged it way down because that took so much time. So that's what's happening here, maybe more intuitively. What's the average speed for that here? Because we didn't change direction, it's the same thing, 40 kilometers per hour. Those two things can be different if we're going in the negative direction, because speed doesn't care about that, or if there's turnarounds, or both. But here it doesn't matter. I think the book indicated here, they just nodded to that this is a vector, because it's velocity, by putting a plus sign in front of it. I don't care if you do that or not for these. Part C, graph x versus t, and show how average velocity is found. So different ways we could do this. Here's one way. If this is position and time, so if that's 40 kilometers and then this is 80, that's the whole trip, right? So we could just map out the time. If this is like 1 hour and that's 2 hours, then at 1 1/3 hours, that's this. And then in that 2/3 of an hour, the remaining 2/3, that's where we did that. And I think they're just, what they're looking for here is they want to nod to the what we've been thinking about a lot in calculus, that the slope of this is the average velocity, right? So it's the slope of that secant line there. That's the average velocity. We know what the slope is of that. It's 40 kilometers per hour. Number 5. The position of an object moving along an x-axis is given by x equals 3t minus 4t squared plus t cubed. where x is in meters and t is in seconds. Find the position of the object for the following values. Okay, let's just go ahead and do that. It should be easy. So the position for A, they want at 1 second. B, they want it 2, 3, and 4. Physics is always calculator allowed. So one thing you could do, unlike calculus, which is often calculator not allowed, you could go here and put this in 3x minus 4. Your calculator wants these to be x's, so we don't mind that. We know that they're really t's for us. Oops, plus x cubed. Okay, and then you can go to, since we just need to plug 4 things into this, there's different ways you could do that. You can go to the table, but before I go to table, I want to set the table, set it up right. I could say, oh, let's start the table at 1 and have the table go up by 1s. That would be one way to do it. The other way to do it would be to leave it in ask mode, and then you could just type in 1, 2, 3, 4. But I'm going to do it that way. So there's my 1, 2, 3, 4. 0, negative 2, 0, and 12. You probably could have done that in the same amount of time, or maybe even less, just by doing it in your head or by hand. So whatever. What's the object's displacement between time 0 and time 4? Well, displacement is equal to final minus initial. So between 4 times 0 and time 4 would be this. So that's 12 minus 0. That's 12 meters. These are all meters, they told us. Right. The book made a point of saying this is plus 12 meters. It's 12 meters in the positive direction. That's implied as far as I'm concerned. F, what's the average velocity for the time interval from time 2 to 4? So average velocity is equal to delta x over delta t. And we're talking here about from time 2 to 4. So that's going to be x of 4 minus x of 2 over the 2-second interval. So let's see, 4 minus 2, that's 14 meters over 2 seconds, or 7 meters per second is that average velocity. And is that it? Oh, G, they want to graph x versus t for 0 to 4 and indicate how the answer for f can be found in the graph. So I'm going to skip that. You could make the graph. You use your calculator to help you do that. And then the answer for f is connect from time 2 to time 4 and find the slope of that secant line. Right. Number 7. Two trains, oh here we go, each having a speed of 30 kilometers per hour headed at each other on the same straight track. A bird that can fly 60 kilometers per hour flies off the front of the train. This is a famous problem. This is a great example of like the easy way and the hard way of doing something. So the trains are 60 kilometers apart. So here's train 1, here's train 2. It really is very helpful, very good practice in physics to make nice little pictures, diagrams of things. They are 60 kilometers apart, and they're going 30 kilometers per hour toward each other. So here's a question. How long does it take before they hit? Well, in 1 hour, this one's going to go 30, and this one's going to go 30, and that's the 60. So their collision at t equals 1 hour. And once you know that, if the bird is flying 60 kilometers per hour, well, the two trains collide after 1 hour. So that means the bird is so I know that the bird is flying at 60 kilometers per hour. Fast bird. And I know that the distance covered is 60. So it takes an hour. The bird's flying for an hour, right? I mean, the trains crash into each other after an hour. And what's the total distance? Oh, I guess I did this. I guess this is the other thing that I knew. I knew that this was 1 hour, and this is the thing that we were looking for. But in 1 hour, the bird's going to fly 60 kilometers because that's how fast it goes. So you don't have to do this crazy, like, okay, where's this train, and then it turns around, and then where's this train going to be after it turns around, and all that. It sets up into a cool geometric series problem if you do that, but the answer is still just 60 kilometers. So that is the easy way to do that. We like easy ways. In 1 kilometer races, runner 1 on track 1 appears to be faster than runner 2 on track 2. However, the length L2 of track 2 might be slightly greater than the length L1 of track 1. How large can that distance be for us still to conclude that runner 1 is faster? Okay, that's a little tricky. So let's see. For runner 1, let's organize our information here. With time 2 minutes, (27.95 seconds), which is equal to 147.95 seconds. I think that's probably going to be better. And runner 2 on track 2 has a time of 2 minutes, 28.15 seconds. All right, so how big can the difference, and this is a 1 kilometer race, right? Okay, so we want to be able to conclude, so how big can that difference be so that we still conclude that runner 1 is faster? So this is like a borderline condition, like how big can it be, how much can you max out that distance, making this person's track longer so that they're actually going faster than what it would appear. So we want to set things equal to each other. So if we say that, and the reason, sorry, let me pause there. The reason why we want to set things equal to each other is we're trying to push that difference up to the extreme. Like, how big can that difference be so that we can still say this person is faster? Well, to figure that out, we're going to push it all the way up to the borderline condition where they're equal to each other, and you can't say that anymore because it will have to be, greater than or less than that boundary value. So that's why I'm going to set things equal to each other. So the distance, let's say the distance of track 1 is 1,000 meters. And let's say the distance of track 2 is 1,000 meters plus. I'm going to use, just like in calculus, we use that little distance h, some little bit of a difference h. And I'm going to set their velocities equal to each other because that's the border condition. So Vx and Vx, they're the same. So what does the equation look like for this? Well, I know that Vx for runner 1 is equal to delta x over delta t. And I know that the Vx here, which I want to be the same, is delta x over delta t. And then algebra. So let's see what happens here. So multiplying this, and multiplying this, algebra. So h is equal to 0.0. Oh, wait, hold on. I messed that up. So the 200 there, sorry, 200 should have been divided not by that, but by this. That still has the decimal in it. So I think I just need to multiply that by 1,000, right? 200 divided by 147.95. So 1.35 meters. If you found that some other way, if you somehow puzzled your way to the correct answer, that's great. That happens a lot in physics, that there's more than one way of doing a problem. Okay, 11. You are to drive to an interview in another town at a distance that's 300 kilometers away on an expressway. Interview's at 11:15. You plan to drive at 100 kilometers per hour. Okay, I got to write down some information here before I go any further. So distance to the interview is 300 kilometers. And interview's at 11:15. Okay, and we leave at 8 a.m. You plan to drive at 100 kilometers per hour. You drive at that speed for the first 100 kilometers. So that's the first. I'm going to make a little 100 on my number line there. This is at 100 kilometers per hour. So that takes an hour, right? But then construction work forces you to slow down to 40 kilometers per hour for 40 kilometers. So up to the 140 mark. And there you're only going at 40 kilometers per hour. So 40 kilometers at 40 kilometers per hour, that also takes an hour. What would be the least speed needed for the rest of the trip to arrive in time for the interview? Okay, I think that's pretty easy to figure out. So here, if this takes an hour, then it is now 9 a.m. here. And if this next 40 kilometers at 40 kilometers per hour, that takes another hour. So now it's 10 a.m., which means that if you want to be on time, you got to get there at 11:15. You have to cover the rest of the distance, which is 160 kilometers, in an hour and 15 minutes, which is 1.25 hours. So that is 160 divided by 1.25, 128 kilometers per hour. You want to know what that is in miles per hour, just to see if we're speeding or not? Well, let's see. To do from kilometers per hour to miles per hour, I know that there's 1,609 kilometers in 1 mile. You should know that. That's a good conversion to know. So that's meters, sorry. So that's meters in a mile. So that's 1 point. So divided by 1.609. So that's 79.5 miles an hour. I can't say I've never driven 80 on the interstate. All right, 13. You drive on Interstate 10, speaking of interstates, 10 from San Antonio to Houston half the time at 55 and the other half at 90. On the way back, you travel half the distance at 55 and the other half at 90. What's your average speed? And what is, for both ones, for the entire trip? What's your average velocity for the entire trip? Sketch the graph of x versus t. All right. And then how can you find average velocity from that sketch? What's the slope? We know that. I might skip that graphing part, leave that for you. So, all right. So you might be wondering, well, wait a minute. Don't we need to know how far it is from San Antonio to Houston? The answer is no, we don't. That's a kind of cool thing about this problem. A dot there. So this is San Antonio, and this is Houston. Let's just call this distance d, some distance d. So on the way there, you take half the time at 55 kilometers per hour, and then the other half the time at 90 kilometers per hour. All right, so let's see if we can figure that out. So I know that my average velocity is equal to total distance, total displacement, but we're going in one direction now, so it's the same. So the total is d, and the total time is the total time t. So what am I supposed to do with that? Well, I know here that that for this part of the trip, that v is equal to 55 over t over 2, and for this part, I'll call that v1, and v2 is 90 over t over 2. That's 110 over t, and this is 180 over t. That's just algebra there. Let's see, how is that going to help us? The total distance. So, oh, wait a minute. I messed this up, didn't I? This is the, sorry, that's what's happening here. This is, I need to solve my, I need to leave this. Delta x is equal to v times t. So I think I messed this up, but not by a whole lot. So I know that my delta x here is equal to 55 times t over 2. There we go. So 55 times t over 2. That's my velocity times t over 2. And then my delta x here is 90t over 2, which is 45t if you like to simplify things. Okay, so there, my here, plugging that in here for the total distance. My total distance is the sum of those two. So that's 55t over 2 plus 90t over 2, or 145t over 2 over t. So 145 divided by 2 is about 72.5 kilometers per hour. right? And that's actually the average of those. If you see what happened there, that's for part A. But for part B, now we're doing, so this is, part B is more like what I was doing there. I was getting ahead of myself. Part B, we want from Houston back, and that's where we did half the distance. Okay, so on the way back, then I know that I'm doing d over 2 at 55, and then d over 2 at 90. So the thing that I don't know, I've got my x and I've got my v. So what's t equal to? If I rearrange this and solve for t, t is equal to delta x over v. So delta x over v, delta x, half the distance, right? That's those two. And then if I come back to here and try to find my average, then the total distance here is d, and the total time is, oops, d over 110 plus d over 180. And the d's are going to cancel out. There's a small amount of work to do here. Basically, I end up with this fraction 1 over 110 plus 1 over 180. And you can jam that into your calculator. So 1 divided by 110 upside down plus 180 upside down. That's about 68. There. And then C, what about for the entire trip? Well, for the entire trip, I'm doing the same distance. I think that for the entire trip, I'm doing the total distance, which is, and this is the average speed, so I'm looking at the total distance. I don't care that I turned around. Is that correct? Yes, average speed. So the speed, that's the total distance, which is going to be 2d, divided by the total time. And again, the time is just the distance divided by the velocity, right? Time is the distance divided by the velocity. So on the way there, the distance is this, divided by 72.5. On the way back, so it sets up just like this one, or 68. So let's see. The d's all cancel out, and I get 2 over 72.5 upside down plus 68 upside down. That's about 70. And part D, what was the average velocity for the entire trip? Well, average velocity is displacement over time, and the displacement for the entire trip, well, you started in San Antonio, went to Houston, and then back again, so your total displacement is 0. And the time is whatever the time took, but it doesn't matter. That is 0 kilometers per hour, because you didn't go anywhere in the end. And sketch x versus t, assuming the motion is all in the positive x direction. And assuming the motion is all in the positive x direction. That's kind of a weird thing to do. So let's make a rough sketch of that. So I guess if everything's in the positive x direction, then there's the distance from, like this is San Antonio, and this is the distance to Houston, and then this is that same distance back again. So let's see, on the way there, we did half of the, was it the time or the distance here? Here it was half of the time. So half the time, half the time. So here, half the time, the first half was at the slower speed, and then steeper, like that. And then here, it was half the distance. So there, we did the slower speed for half the distance. So it's something like this. And then if you're, where are the answers to all these questions? Well, the answer for question A would have been the slope of this. The answer for B would have been the slope of this. The answer for C is the slope of the, from here to here, from beginning to end. And you can't really see the answer for D in here because we took everything to be in the positive direction. So we got that for piecewise linear thing there. All right, that's a big problem. If you're starting to stress out at this point, you're like, holy crap, physics is really hard. These are hard questions for constant velocity, and I'm not going to throw anything like that at you on the test. But these are good problems to puzzle through. Makes us feel good about things if we can do these. So 15 and 17 kind of don't belong here. This is really a little bit of calculus, so if you're like, wait a minute, what were these problems about? This is a little bit of, to go with calculus stuff that we're doing right now. For 15a, if a particle's motion is given by this position equation, t is in seconds, x is in meters, what's its velocity at time 1? What is its velocity? They're not saying average anything. So how do you find that? Well, velocity is dx dt. It's the slope of this, and I know how to do that now. Right? It's just the derivative. So what's the velocity at time 1? Velocity at time 1, plugging 1 into this, is -6 meters per second. Is it moving in the positive direction? It's moving in the negative direction, because that's a negative sign. And what is its speed just then? The speed is 6 meters per second. The speedometer on this thing isn't going to register the negative, so the speed is just the absolute value of that. Is the speed increasing or decreasing just then? Okay, so that's a little tricky. With what we know right now, maybe the best way to answer that is just to try to figure out, well, what's the speed like a second later? So the speed is -6 meters per second, and what would the speed be? That's at time 1. At time 2, then it's going to be 0. So it's going to be going from -6 to 0. But we're talking about the speed. If you're going -6, your speedometer says 6, and then if you go down to 0, you're slowing down. You're going from having a speed of 6, even though it's negative, to slowing down to 0. All right. Let's see. Lost my spot there. There we go. Is there ever an instant when the velocity is 0? Yeah, we kind of just figured that out by accident there at time 2. Right? And F, is there a time after t equals 3 when the particle is moving in the negative direction? So let's see. When t is equal to 3, this is 18, and if we go forward in time from there, it's only going to get bigger. I mean, we could actually make a graph of this, right? That's just a straight line, the velocity. But clearly, if we plug in 3 here or anything bigger, that's going to be positive. So their question was, is there a time? No, there is not. Answer no, they said. So we will answer no. All right. Calculus. And then 17th position of a particle moving along the x-axis is given by this. T is in x is in centimeters and t is in seconds. Calculate the average velocity during the time interval from t2 to t3. So average velocity is delta x over delta t, and they want from, I think it said from 2 to 3, right? So that'd be x position at 3 minus position at 2. Yep. Over the time interval, well, the time interval, like, you can write a 3 minus 2, but 1 second goes by there. So plugging 3 in here, I think I'm going to be plugging a bunch of numbers into this, so I'm going to go ahead and put it here, 9.75 plus 1.5x cubed. And I'm going to go to my table set. I'm just going to put it in ask mode, so I can just type in whatever I need to. So let's see, I need to plug in 3. And then plug in 2. And then do some math. 50.25. We could probably do that without a calculator, but it's in my hand. I mean, come on, give me a break. 28.5 centimeters per second. I did say it was centimeters. Okay, B, they would like to know what is the instantaneous velocity at time 2. Well, the instantaneous velocity, the derivative of this, that goes away, power rule on that. So the velocity at time 2 is 2 squared is, let's see, 4.5 times 4, 18 for B. Part C, it's the instantaneous velocity at time 3. Plug 3 into that. That'd be 40.5. Oops, forgot to write my complete sentence. That's at time 3. 40.5 centimeters per second would be the answer for part C. And part D, we want the instantaneous velocity at time t is 2.5 seconds. This is too easy. 4.5 times 2.5 squared. That's about 28.1 centimeters per second. And E, the instantaneous velocity when the particle is midway between its positions. Oh, that's a little trickier. Okay, so the instantaneous velocity when the particle is midway between its positions at time 2 and time 3. Well, let's see. There's its position at time 2 and time 3. I don't even know what those, oh, I do know what those are because I found them here. So what's midway between those two? I'm going to just average those. This is a position at 3 and a position at 2, so I need the midpoint of that because that's what they said, midway between its positions. 50.25 plus 21.75 divided by 2. So that's 36. So but I don't know that that happens at the mid-time, right? That would be true if it was going at constant velocity. That is the mid-location. All right, so instantaneous velocity when. So I think I need to figure out when is it at this place. So when does that happen? Well, I have the position function here. So 36 equals 9.75 plus 1.5 t cubed. I'm going to do a little bit of algebra. 36 minus 9.75, and then I need to divide that by 1.5, and then I need to take the cube root of that, or raise it to the 1/3 power. That's another way of doing that. And that gives me a time of 2.60, rounded to 3 sig figs. Okay, that's the time. And then they want the instantaneous velocity at this time. So then I just need to take that time and plug it into my instantaneous velocity. So that number squared times 4.5. And that's about 30.3 I'm getting. And then last, I think they want another graph x versus t and indicate your answers graphically. So I already got it there. So let's see, what kind of window would I want here? On the x-axis I have time. I think I'm interested in times from 0 to 3. And then the positions here, I'll go from 0 to, what's the biggest position that I had for any of these? At 50.25 at time 3. So maybe I'll go up to 60. So I'm just going to make a sketch of this over here. I'm not going to fuss too much. So my times and then this goes up to about 50. It's x in centimeters, time in seconds. So let's see, when it starts out at 9.75, so if I scale that by 10, so that's about there, and then it looks like it bends up like this. So what are we looking at here? The answers for these things from time 2 to time 3, that was an average. So for part A, it's a secant line. For parts B, C, and D, that was the slope of the tangent, or for B and C anyway, that's the slope of the tangent line here and the tangent line here. And then D, that was the tangent line right halfway in between them. And then for E, it was a little bit past that, so you'd have to sketch in the tangent line. It's getting a little messy here. But those are all slopes of secant lines for average velocities and slopes of tangent lines for instantaneous velocities. Calculus. Yay!